Hello, my name is Jared Skeens and welcome to the Zoom room. Today we'd like to cover Pure Maths 1, Integration, Part 3, and this will be the first of our Volume of Revolution videos where we focus in this video on the x-axis, and then in the next video we'll look at the y-axis. So what I have here in the top, actually I could have shared this back in part 2 with area, but it's extremely important, especially as we move into volume of revolution, that you have a strategy in your mind as you work through these a little bit complicated problems. So this is my general guideline that I follow to help me stay on track with these problem types. And that is simplify, integrate, and evaluate. I'll explain that as we go, but I would write that down in your notes. When you're working with integration, you want to simplify. If there's something to simplify, simplify first, integrate, then evaluate. Make sure you pay attention where you're at in this progression, and it will help you get that long-term goal achieved. Now, as far as formulas, what we're looking at is volume. Now, we looked at area in part 2, so let's just start with that. And here we have a graph, x-axis, y-axis, and we have this triangle-shaped area shaded in, and we have this function here. Function equals 1/5 x, so it goes through the origin. And that is our main function we're looking at. And the shaded region is between the boundaries of 0 and 5. So whether this line is actually shown or mentioned that the boundary is the x equals 5 line, here's our boundary here from 0 to 5. Now, when we were looking at area, we saw that area is height times width. And so the height, and remember I suggest that you draw a representative rectangle. And what I mean by representative is you're slicing this area into basically an infinite number of slices. And so we're just going to draw one rectangle. And the height of it, you can see, goes from the x-axis, and it comes all the way from the x-axis to the function itself. So the height of this rectangle is determined by f of x. Wherever this rectangle's at in this area, the height of it is f of x. The width of it is delta x. Delta x is the change in x. So you can make it as wide or narrow as what you want. But remember, as we do integration, we're driving that delta x towards 0. In other words, we're making it really, really small so that we can get almost like an infinite number of slices here through this area. And the smaller the slice, the more accurate our approximation will be. So the formula for area then is the integral from the boundaries a to b, and the f of x is the height, and the delta x is the width, and height times width gives you area. So that's what we did in part 2. Now we want to expand on that a little bit, and we want to see how we can get the third dimension in, that's volume. So with volume here, with volume, what we want to do is rotate this graph around either the x-axis or the y-axis. So when you rotate something to get the third dimension, area is two-dimensional, which is why we can show it on the board. Areas, so length is one dimension, basically, one-dimensional. You add 2 dimensions, your x, y axis, you now have area two-dimensional. We want that third dimension. So these question types are going to ask you to rotate the graph or the shaded area 360 degrees about an axis. This part 3, we're looking at x-axis. Part 4, we'll look at the y-axis. Okay, so the first thing I do is I show the rotation. So we're going to rotate this around the x-axis. Okay, so if we take this object and we rotate it, then if you come down here to the where it's touching the x-axis, and that's like our central pivot point, and you rotate it, you're not moving anywhere, right? So if you rotate your x-axis and you're right at the x-axis, the point of it, you're not moving anywhere. But if you're away from the x-axis and you rotate around the x-axis, this is going to create kind of a circular effect here. So I don't know if I'll be very good at this. Sorry, my three-dimensional drawing is not that great. So we're going to get this circular end here. And that means that this is kind of reflected, so that this line up here, as it rotates around, is kind of like going down here. And so now we have this circular shape to it. And that's why this is called the disc method. Generally, there's about 3 methods of dealing with volumes of revolution. There's disc method, washer method, and there's also something that some people call shells, some people call cylinder method. And fortunately, Cambridge has not gotten into the cylinder method. We'll talk about the washers here in a minute, but most of what they give to you is the basic disc method. So here we have, notice that when we rotate this around, we get this circular shape here. Okay, it's at the end. You see that circular shape there? And as we have our representative rectangle also, now this representative rectangle is also rotated. I don't know if I'm very good at this, but here you can kind of sort of hopefully see that you get a little bit of a disc there. And so the side view is a circle. So we know that a circle, the area is pi r squared. And then the third dimension is our delta x, the thickness of the circle. So if we rotate it around the axis, we're making a circle, and then we take a slice that's delta x wide, that gives us our volume. So it's almost like taking a cylinder that's circular on one side and has a height of dx. If you were to pull this out, set it sideways, it'd be like a flat cylinder. But this is called the disc method. And so when we start making this a formula, we have the pi, and pi is a constant. So the constant can actually come outside of our integral sign. It doesn't affect it. It can be applied later. So there's our constant, the pi. And the radius of this now circle is defined by the height. Okay, the radius is defined by the height, which is function. So we want the radius, which is now our function, and that radius goes above and below. And sorry, my dimensional drawing here, maybe that's a little better. Here, this disk is delta x wide. That's the thickness. And the circle here, the radius, is the function itself. So our formula is pi, and then the function is the radius. Oops, sorry, I was using blue. Let me put it in blue so we don't confuse the red here. So the function is the radius. Okay, and then the thickness is the delta x. So we have pi r squared dx, and so we move from our circle formula, which is pi r squared, and now when we add on the thickness, the dx is kind of like the height, if you will, if you want to call this height and make this more like a cylinder, or it's a disk, you know, pi r squared, and then the height, however you want to look at it, that dx is the thickness of it. So this isn't called the cylinder method, it's called the disk method. Cylinder method is something conceptually similar but different. And so that's our thickness there, is the dx. So whatever one that you choose to represent that. So this is the formula that you need, pi r squared, and then the thickness for the disk. Now, let's continue on with this and show how it works. If you notice this triangle, when this triangle was rotated around the x-axis, it creates a cone-shaped, pointed at the front, circular at the back. We know the formula for cone. I did the same thing for area, started off with a familiar geometric figure. So our familiar geometric figure is now a cone, and we have 1/3 pi r squared. So 1/3 pi r, our radius at 5. Plug in 5 times 1/5, you get 1. So at the circle part at the bottom, our radius is 1 squared times the height. The height would be this way from 0 to 5. So our height is 5. So 1 squared is 1 times 5 is 5. 5 times 1/3 is 5/3 pi would be the volume of this cone. Easy to do because it's a fixed geometric figure that we're familiar with. Obviously, when you get into curves, you no longer have a nice formula for it. So if we do the same thing using integration, again, I follow this format: simplify, integrate, evaluate. So I've got it split up by these 3 words up here. So the first thing we want to do is plug it in, pi, integrated from the bounds of 0 to 5. Here's our radius, is the 1/5 x. So pi r squared, and then dx. Well, because we're squaring it, we need to simplify this first, or it would make it easier to square things out. And so when we square it out, we get 1/25 x squared. So this is the simplify part. So we still have pi 0 to 5. We've now simplified, we've expanded out the square, 1/25 x squared, and here's the dx. Now for the integrate. So you add 1, you get 3, that's the x cubed. You divide by that number, so 1/25 divided by 3 is 1/75. So we have pi 1/75 x cubed, and this has been integrated. Our bounds are still 0 to 5. So that's the integrate. Now we evaluate. Remember, top minus bottom. So we plug in the 5 cubed minus, and this actually should be 0 cubed. Okay. So 5 cubed is 1/25 over 75 pi. 0 just makes that 0, goes away. And 1/25 75ths, 125 75ths reduces to 5/3 pi. And notice we have the same answer as our volume of a cone formula. So that's how it works. Simplify, integrate, evaluate. This is the concept. rotating it 360 degrees, that creates the circle, pi r squared. The volume is the thickness, our representative rectangle of delta x. And we are taking that volume in a pi r squared delta x by integrate it, meaning we're taking an infinite number of slices because our delta x is being driven or approaching zero, meaning it's really, really thin, each slice. Okay, so it makes it more accurate. And as you can see, we got exactly the same value. Now, this is just the illustration. Obviously, a Cambridge question will not usually give you something that you already have a fixed formula for. They're going to give you curves. But I wanted to at least illustrate it with something you can relate to. Now let's talk about washers here really quickly. I'm going to share screen. There's only 2 questions that I've found in the last 10 years of past papers that have washers. But since it exists, I'll at least mention it. You can look them up yourself and try to, be like a nice challenge problem for you. I do provide the formula here, and I'll give you an illustration. This here is a washer. We'll talk about that, but let me share screen here for a second. Now, if you notice this, here is volume of revolution for washers. This is actually one of my worksheets for my students. And here you see the shaded region. Now, notice it says find the volume obtained when the shaded region is rotated through 360 degrees about the x-axis. If you rotate this around the x-axis and you start here at point B and rotate it around, you're going to get a circle here. And then you come up here to point A and you rotate it around the x-axis. You're going to get a bigger circle there. Here's your shaded region. So this line here, when you rotate it, is going to show up down here like this. And when you rotate this curve, it's going to show up down here like this. So you're going to have a curve and a straight line. Your shaded region is going to be in here somewhere. But right in here, you're going to have an empty space. Okay, that empty space is a hole in your volume. In other words, the volume is not solid all the way through. You've got solid here, but down here as it rotates over the x-axis, all this is empty. So let's come back here, and here is our disk. If our disk was solid all the way through, you see that you have a circle, that's your pi r squared, and then the delta x is the width. And of course, we're trying to make it very thin so that you get more slices because it makes it more accurate with the graph as you draw your rectangle up to the graph. So that's the delta x right there. And here is the disk, the pi r squared. Well, if you're dealing with a graph that when you rotate it, creates that hole in the middle, you need to pay attention to that. Although, like I said, it's rare. So I hope you saw, let me share again really quickly. If you want to look it up, S17, so summer of 17, paper 12, number 6, that is your x-axis example of washers. You can look it up yourself, try it, be a nice challenge for you. Here's the formula. It's still pi r squared dx, essentially. But now you have 2 radii. From the center of the circle, which would be your x-axis is going through it, and you've rotated it around the x-axis. So your x-axis would be going through like this. So from your x-axis outward, you have the outer radius. And then from the center to the edge of the hole, you have your inner radius. So what you need to do, if you run into these, and like I said, it's rare, there's only 1 question for x-axis and 1 for y-axis for the past 10 years of Cambridge papers, but it is possible. You take the outer radius, that is the whole disk, pi r squared and subtract the inner radius, which is the radius of the hole. So when you take that circular radius out, you're taking the big disk minus the area of the hole, and that gives you then the area, and then add the dx to it, and that will give you the volume of this washer. So it's called the washer method because this is a washer, and that's what you get. You have an outer radius and you have the inner radius. So this is the formula for that. When I give our first example, I'm going to erase that because most of their questions are just a regular solid disk, okay? And so let's get started. Let me pull up our first example. Okay, here we are. And I erased the washer formula because we want to focus on disk. I left the disk formula up. Again, remember, simplify, integrate, evaluate. That's going to be our kind of overall guideline. Here is our question. Shows a picture of this curve, this graph with this curve, and the equation of this curve is y equals 4 over 5 minus 3x. We also see this boundary here, which is the x equals 1 line. So our shaded region is bounded by the curve, the x equals 1, and then our x and y axis. So they call it the coordinate axes, and then x equals 1 and this curve up here. It says find the volume by rotating the shaded region 360 degrees about the x-axis. So the first thing that I'm going to do is I'm going to draw myself a little rotation thing here. It's helpful to me to see which axis I'm rotating it around. Now, I've already drawn it, but the second thing I do is I draw my representative rectangle. And what's important for this, especially as we look at the difference between x-axis volume and y-axis volume, is since we're rotating it around the x-axis, my rectangle has to be connected to the x-axis, meaning this is a delta x. And it's coming off the x-axis, and you can see that the height of the rectangle is defined by the function. So as you move this rectangle across the shaded region, the height of it is determined by our function. This is our f of x. That's the height. And the delta x is because it's along the x-axis, which is our axis of rotation. So this entire graph is being drawn around here, meaning we're going to get over here a little circle like this, and over here we're going to get a bigger circle like this. My three-dimensional drawing's not that great. I realize my circles are kind of facing opposite ways, but hopefully at least it gives you the idea that we have circles at both ends there. So that's our pi r squared. And then the delta x is the thickness that gives us the volume. So now that we've done that, again, I draw the rotation on the appropriate axis, and I also put in my representative rectangle also connected to the appropriate axis. Now we need to follow the formula. Let's set up our formula first. So we're going to have pi, and it can go outside the bounds of the integral sign because it's a constant. Now we have our bounds of integration from a to b. Well, that's from 0 to 1. Remember, this is the 1 line. So from 0 to 1. Then our radius is the height, which is the function itself. So our function is, and I'm going to bring it up as an exponent. Remember, every time we derive or integrate, we want to put it in exponent form. So this will be 4 times 5 minus 3x to the negative 1 power. So this, we bring it upstairs or to the numerator and give it a negative 1 power. So this then is the radius, because it's the function that defines for us how far it is from our x-axis, the radius. And we need to square that because it's pi r squared. So don't forget the square. And then dx makes our third dimension. So pi r squared is two-dimensional, and our third dimension is the change in the x, or the thickness of our disk. Okay, so the first thing that we want to do is simplify. That's this part. In other words, we're going to carry out or expand this square. So what we get is pi, still have our integral, we haven't integrated. So pay attention where you're at, 0 to 1. Now the square distributes to multiply. So the square on the 4 makes 16. Then on this parentheses, it has an exponent, -1, and when you raise an exponent to an exponent, you multiply. So -1 times 2 is -2. So 5 minus 3x to the -2, and then our dx on the outside. So all I've done is distributed the square to the 4 and then to the exponent. So remember, exponents distribute to multiply. And so this is now simplified. This 16, if you want, the 16 can come out in front with the pi, or you can leave it inside. It's up to you. Let's bring it outside so that we can focus on the parenthesis there. Some people find it easier to remove that coefficient. So now we want to integrate. So we're going to have 16 pi times, and now we're going to integrate this. So remember, we add 1. So -2 plus 1 makes a -1. So we have a 5 minus 3x to the -1 power. We divide by that number. So -2 plus 1 is a -1. So we divide by -1. And don't forget, this is expanded form, meaning we need to also do the derivative of the inside, which gives us that -3. It's not the 5. Notice the x is in the back, not in the front. So be careful. Don't just put 5 because you're used to it being in the front. 5 disappears. It's a constant. When you integrate, the derivative of the inside, when you take the derivative, the constant disappears. So the 5 disappears, and the derivative of -3x is -3. So with integration, we divide by that -3. Okay, so we added 1 to the exponent, we divided by that value, and then we took the derivative of the inside and divided it by that. So let me make this a little bigger. So this then is going to be evaluated from 0 to 1. But before we evaluate it, let's clean it up a little bit. So you kind of need to simplify as you go, but we have already integrated, which is why our integral sign is gone. So this becomes 16 pi. And actually this +3, -1 times -3, could also come out front, again, because it's a coefficient. So what we have here is this 5 minus 3x to the -1, and we're going to evaluate it from x equals 0 to x equals 1, from 0 to 1. Okay, so I just cleaned it up a little bit so we can focus on the necessary part. Now we're going to evaluate. So this is all simplify. This was the integration, and then also simplified after we integrated it. Now we want to evaluate. So we get 16 thirds pi times and we have to plug in a 1. So when we plug in a 1, we get 3. 1 times 3 is 3. 5 minus 3 is 2. So we get a 2 to the negative 1 power, which is 1/2. Remember, top minus the bottom. So we plug in a 0. Notice it does not become 0. 3 times 0 is 0, but 5 minus 0 is 5 to the negative 1 power is 1/5. So that equals 16/3 pi. And if we do this in tenths, that would be 5 tenths to get common denominator. Again, you can use your calculator. I'm just showing you without the calculator. So 1/5 would be 2 tenths. So that means this in here is 3 tenths. So we get 16/3 pi times 3 tenths. The 3's cancel, so we get 16/10 pi, which reduces to 8/5 pi, which if we put it to 3 significant figures is 5.03 to 3 significant figures. So you can put 8/5 pi. You can also put 5.03 because it's the 3 significant figures. Either one will be acceptable. But here is how you do volume of revolution. Notice we do not have a nice fixed formula for this shape like we did the cone. And again, that's where calculus really benefits us because it deals with a changing concept, something that's changing on us as we go. And so since it doesn't have a fixed formula to it, we can calculate it using integration. So again, the main thing, simplify, integrate, evaluate. Make sure you're carefully following those steps. I notice sometimes people simplify and all of a sudden they think when they simplified, they already integrated and they go straight from simplification into evaluation. So careful to follow step by step through it. Okay, this one was pretty basic, not easy, but not too difficult. We'll do one more example that will definitely be a little bit more challenging for us. So let me set it up for us. Okay, here we are. And notice we have quite a complicated problem here. In fact, this particular problem is worth 8 points. So you really want to pay attention to your mechanics, that is executing your formula correctly. You also want to pay attention to your general mental guide as to your steps and where you're at in this process, because this is a little bit more complicated. And what I notice is that a lot of students, when they get to these complicated problems, either they lose track of where they're at and they end up skipping steps, or they get intimidated by the complexity of the problem and they end up jumping all over the place. And it's like they're trying to just get the answer and get it done. So you really need to be patient and be thinking clearly. Make sure you're training your mind what to look for and slowly work your way through. You can't too slowly, but you need to systematically work your way through the problem and make sure you're doing it correctly. Okay, so what makes this particular problem more challenging is you might notice that I have 2 representative rectangles here. We'll get to that in a second. The question says to find the volume of the shaded region as it's rotated 360 degrees about the x-axis. So again, the first thing I show is my little rotation here. So I see that this is what I'm rotating it around, or rotating this way. And so that means over here, this rotates down here and makes a circle like that. And this over here also rotates down here and makes a circle like that. Again, I apologize for my terrible 3D drawing, but you get that circle as you rotate it on both ends. It's just a visual aid, and I hope it's helpful. But you get that circular effect. It actually looks rather ugly, but maybe we can thin it up here a little bit. Maybe that's a little better, not much. So now I put in the angular rotation. We're making our circle this way around the x-axis. And I put in my representative rectangle here. And notice there's two. And the reason why there's two, you want to make sure that when you put in your representative rectangle, whether you're dealing with area or volume, that your rectangle can be the same function all the way through. The height is f of x. But if you notice, if you start here in the left-hand side, the height is this line. So as you move across this representative rectangle, you reach this point right here. Now all of a sudden, your line is going up here, but the shaded region is going down, meaning I've got a new function now determining the height. The line does not determine the height of this one, and the curve does not determine the height of this one. So I need two representative rectangles, one to show the connection between the x-axis and this function, and one to show the connection between the x-axis and the curve. So what that means is we're going to have to divide up our boundaries. So instead of going from 1 to 3, notice point A is at 2, 3. So I'm going to put a dotted line right here. We're going to split this up. We're going to have to do two integrals because we have two separate functions and we can't combine them. So we're going to have to do just the same thing twice. So we'll actually find the volume of this one, and then secondly, the volume of this one, and we'll add them together to get the overall volume. So it is a little more complicated. Again, here is our mental guide. We want to set it up, simplify, then integrate, then evaluate. So let's start it up here. Again, we'll put our pi, our bounds of integration. Well, for this first section, this representative rectangle can only go from 1 to 2. Notice it's not at 0. The y-axis is over here. There's x equals 1 line and x equals 3 lines. So it's shown in the diagram, but you have x equals 1 and you have x equals 3 lines that are shown in the diagram. So we have from 1 to 2, which is where this line ends as far as our shaded region goes. So from 1 to 2, and that function is the y equals 1/2 x plus 2. Notice it's linear. This is a line here, and it gives it to you. Actually, there's a part I where you have to show that this is this equation, but it does give it to you. It's a show problem, but we're interested in the volume part. So our function for this section is 1/2 x plus 2. Remember, it's pi r squared, so don't forget the square. And then we have our dx, that's the thickness from our representative rectangle. Plus, we want to add to that the volume of this next section, which is from 2 to 3. And the height of this is determined by this curve. Now notice this curve is a little bit bigger than normal as well. So don't be afraid of it. Just put it in here. So we have an x minus 1 to the negative 2 plus 2. And all of that is our function, or the radius here. And so it needs to be squared. And we have our dx. Okay, so we've set up the problem according to the formula, and we had to separate our boundaries because we have two different functions acting as the radius. Okay, now what we want to do is now move into the simplify part. The simplify means we want to go ahead and expand our squares here. So and this is my recommendation. You could actually go ahead and integrate this without expanding. This one would be more difficult because it has two terms. Since this is only one parenthesis, you could actually treat this as an expanded form itself. But this one is more complicated. I'm going to go ahead and expand it anyway as part of the simplify. I want you to follow that simplify, integrate, evaluate. Later, once you become comfortable, you'll realize that there's a couple of different variations on how you can do it as far as method goes. But this is what I recommend for you to start with. So we want to expand this and do the simplify part. So we're going to have our pi. We're still going to have, not 0, sorry, 1 to 2. And when we square this, remember exponents do not distribute over add and subtract. This is a binomial, so you have to do 1/2 x plus 2 times 1/2 x plus 2. If you need to write it side by side like this, 1/2 x plus 2 times 1/2 x plus 2, and expand it out by smiley face, then go ahead and do that on a separate sheet of paper or off to the side. But hopefully you can, by this point in your AS level, you should be able to expand this out. And it's no problem if you have to do this. So what you're going to get is 1/4 x squared. Okay, so what you're doing is your smiley face method. See your little smiley face there? So you need to expand it out. So you get 1/4 x squared plus, when you multiply the 2 times it, you get 1x, and there's another one, so plus 2x plus 4. That's the expanded, and then the dx. Plus pi from 2 to 3. Now we have to do this one. So this one is like an x minus 1 to the negative 2 plus 2 times an x minus 1 to the negative 2 plus 2, like this. And I understand that this is a little bit more complicated than this one, but be patient and think about, first of all, exponents do not distribute over add and subtract. You have to put it side by side like this. Then think your smiley face method again to help guide you through it. So when you multiply x minus 1 parenthesis times x minus 1 parenthesis, you add exponents. So when you add a negative 2 to a negative 2, you get a negative 4. So you're going to get an x minus 1 to the negative 4. Okay, don't worry about it looking ugly. That's your rule. When you multiply bases, you add exponents. Multiply like bases, you add their exponents. Then this middle one, you have 2 of these, and then you have another 2 of these. So we have 4 of these x minus 1 to the negative 2. Don't try to make this 1 over x minus 1 squared, and don't try to expand it out in the denominator. Keep it up here in the numerator. Okay, so just leave it as negative exponent, and then you have 2 times 2 is 4. And then, of course, we got our dx there at the end, which is our width. So all of this is the simplify. This is the formula. This is the simplifying, which basically was expanding out the squares. Now that we have it term by term, now we can move to integrate. Okay, so now that we integrate, what we're going to get is pi. Now we're integrating, so I'm getting rid of the integral sign. So we add 1 and we divide by that number. So when we divide by 3, we get a 1/12. Okay, so dividing by 3, 1/4 divided by 3 is 1/12. We added 1, so we have x cubed. It's not an expanded form, so we don't have to do, there's no parenthesis here. Here's 1 plus 1, that's now 2 divided by 2, the 2's cancel. So we just get x squared plus 4x. So this is like an x to the 0 plus 1, you get 1 for your exponent for x, and your 4 is your constant. So this then will need to get evaluated for 1 to 2, okay? Plus pi, and again, we're integrating so we can get rid of that integral sign. Add 1, we now have -3. So we divide by -3, so we get a -1/3. And we get our x minus 1 to the -3 because we added 1. And we have an expanded form, but when we derive the inside, the derivative is just an understood 1. So that doesn't really change anything. There's really nothing that we get when we derive the inside, but technically we're dividing by 1. Then we move on to the next one. We add 1. -2 plus 1 is a -1. Pay close attention to the signs of the numbers when you have a negative exponent and you're adding 1. It doesn't make -3, that's going down. -2 plus 1 is -1, you're going up. So we get a -1, so that's a -4, because it's 4 divided by a -1. X minus 1 to the -1. So the -2 plus 1s are -1. We divide by that, which gives us -4. And again, our inside is expanded, but it only gives us a 1 in the derivative. And then we have a plus 4x again here. And this is being evaluated from 2 to 3. So all of this is the integrate part. So this was our formula, this was our simplify, this was our integrate. Now I'm going to get rid of this since we've already multiplied it out. And what we're going to move to now is our evaluate. Okay, so we want to evaluate this. So we're going to get pi times, we plug in the 2, remember top minus bottom. So 2 cubed is 8, so we get 8/12 plus 4, 2 squared, plus 2 times 4 is 8, that's the top one, minus, now we plug 1 in, so 1 cubed times 1/12 is 1/12, plus 1 squared is 1, plus 1 times 4 is 4. So that's the evaluating here, top minus bottom, plus pi times, and we plug in a 3. 3 minus 1 is 2. 2 cubed is 8, but the negative means it goes in the denominator. So an 8 in the denominator makes this a 1/24. Okay, so 3 minus 1 is 2. 2 cubed is 8. But the negative actually makes it a 1/8 or 1/8. So 1/8 times a -1/3 is a -1/24. Here we get minus 3 minus 1 is 2. To the -1 means 1/2. So 2 to the -1 is 1/2 or 1/2. So 1/2 times 4 is 2. So we have a -2. And then 3 times 4 is 12. Minus, and now we plug in a 2. 2 minus 1 is 1. 1 to any power is 1, so we get a -1/3. I'm running out of room here. 2 minus 1 is 1 again, so a -4. And then 2 times 4 is a +8. So I kind of ran out of room there. So a -1/3 minus 4 plus 8. Now we can start calculating it up. So we have pi times, and when we do this first part here, the 8/12 plus 4 plus 8, we get 38 thirds minus, and then when we add up 1/12 plus 1 plus 4, we get 61/12 plus, and when we add up our negative 1/24 minus 2 plus 12, we get 239/24. You're doing this on a calculator. You don't have to do this in your head. I've already got it written down because I did it on calculator. This is too big of fractions for you to do all this in your head. And then minus, and when we do the negative 1/3 minus 4 plus 8, we get a minus 11 thirds. So this comes out to 91/12 pi for this first part. And then for the second part, we have a 151/24 pi for the second part. You can check that out. And that gives us a grand total of 111/8 pi when you add those two together, which if you change it into decimal form is approximately 43.6. 2 or 3 significant figures, and this is our answer. You can have it in exact form or decimal. Although please pay attention to reading the question. Sometimes or every once in a while they do say find the exact value. That means they want the pi, or if it has a radical in it, they want you to keep that and not use the decimal form. So if it's exact, you put 111/8 pi. If it doesn't say that, it's still okay, but you can put 43.6 because it's to 3 significant figures, and that is also okay. So it's a lot more complicated, a lot of work. You got to realize volume of revolution. You know your formula. You set it up, and you just follow step by step. Simplify, integrate, evaluate. Remember, complicated problems are nothing more than a compilation of a bunch of simple steps. So yes, it is complicated when you look at all of it, but when you follow through one concept piece at a time, each piece is doable. You've done exponents before. All of the technical mechanics are things you've done. You just need to conceptually put it together into the string of events that lead to the outcome. So be patient, take your time, think it through, and be very careful with your mechanics of executing the integral, okay? And follow the general simplify, integrate, evaluate, and hopefully you can be successful in these question types. They are higher point value, and this is your big challenge for the Pure Maths 1 is usually your area of volume in the integral. There's a few other challenging ones also, but this is kind of the big showpiece of the Pure 1 Cambridge exam paper, and half of it again is mental. Train your mind mentally, train your skill, pay attention to the details, and you can do it. You can be successful at this. Good luck. Thank you again for joining me in the Zoom room, and I'll see you again next time for part 4, where we'll look at the y-axis.